My name. Well, I wanted to make some mysterious name, and I think what happened is that everybody escaped from the room. So it should have been something more exciting. But it's a survey of what we did with my student, as Matti Tastola and Jesse Holman, over several years, and it's kind of we're known for a quiet environment, and is, still water's right deep. So is water really still, and how does it deep? How deep does it run? So we did some good work over the last several years, and Matti won Paul Getting Memorial Fellowship and William and Leslie Knight Fellowship in Marine Science, and Jesse got Tampa Bay Parrot Heads in Paradise twice. So now it's time to tell you what we're doing. So we're investigating turbulence in various geophysical, planetary, and laboratory environments, trying to see things which are common and different, and trying to learn about one system from another. We're trying to improve our understanding of turbulence on all scales, and they're all interconnected because the problem is very strongly nonlinear, and flows are nonlinear. And we're using analytical, numerical, and empirical tools. The turbulent flows are most common in nature. It, I think, didn't come across this point in previous presentations, but we need to remember this. And they determine global phenomena, global circulation. They determine regional flow configurations, and I'll show some of it. They determine mixing, which is exchange of momentum, heat, mass transfer, climate change, and everything else. In fact, turbulent flows are non-Newtonian fluids because the relationship between mean stress and mean rate of strain is nonlinear. And this is a very difficult problem because the coefficient is by itself flow dependent, known as eddy viscosity. And Bob Weisberg already said it. He attracted attention to the importance of circulation, but inside the circulation, the turbulence is most important natural carrier of chemical, biological, ecological, and processes which are related to life systems, which are more close to marine science. We're using two-pronged research. We have small scales, which are atmospheric boundary layers, and this kind of flows, they link between the flows on high altitude, like troposphere, free atmosphere, with underlying surface and surface processes. And this research is mostly analytical. We've developed an analytical model of turbulence, which is being used, and numerical using the WRF model. It's weather research and forecast model, which is being run in NCAR. And Matti was working in this area, and so far he already published 3 papers, and as one, he published 2 papers. The quarterly journal is in review. They had a problem with reviewer, so it's a little delayed. And he's already working on 1 or 2 more papers. On large scales, we actually look into the variety of oceanic, atmospheric, and planetary jet flows. But we are doing this in the laboratory facilities. Because Jesse is a very good experimentalist. So we already have 1 paper which is in press in JRL, and there is another one coming, and then I'll show you what we shall do next. So I'll start with atmospheric boundary layer. As I said, atmospheric boundary layers relate troposphere and free atmosphere to the underlying surface. It can be land, can be water, can be ice, can be anything else. So it's a boundary layer. It's kind of a medium between the air and the underlying surface. What we know is that when we use model for this kind of flow, we need to have a model which is consistent between what it's doing in non-zero elevation and near the ground. This may be tricky because we know that there is a no-slip condition near the ground. Velocity goes to 0, and it goes from some non-zero value. So the gradients near the ground will be very large, and it's not easy to create a model which will handle gradients like this. if we have inconsistency between the model and the near-ground processes, then we can produce artificial fluxes, so momentum, potential, temperature, humidity, and they will degrade the quality of the forecast. So what to do in this case? We can develop near-surface model from the general model, but we need to use some self-consistent approximation and to develop some simplified model near the ground from more complicated model equations on higher altitude. And when we do this, we develop so-called Monod-Nabokov similarity theory. The theory uses some special functions, and this is what links near-surface parameters to parameters above the ground. This consistency is crucial, because if it's inconsistent, then we shall develop some spurious fluxes of momentum, heat, and whatever. So we looked into the importance of consistency between, in different models. One of the characteristics to test the consistency and performance of the model is so-called Deacon numbers. They're developed here. They're based on second derivative of temperature and velocity, and you can this thing phi m and phi h are stability functions of Monod-Nabokov function, and because they depend on the second derivative, they're very difficult to measure, and it's very tricky. And when you look on the data, there is a lot of scatter in this data. So this is what happens. This is 4 different databases, and the points are everywhere. Okay, but there is some tendency if you look at it. And now here are empirical models which are used to represent these points, and some of them work in some range, but then they go completely wild in other ranges. And this is our analytical model QNSE, quasi-normal scale elimination. And this model it doesn't have any any tuning coefficients. So this is something which we can test physics against the data. So this is the result of QNSE. And you can see that it covers the data, at least it covers the tendency pretty well for velocity and for the temperature. Other models do very strange things. They go like this. I mean, you can find some good region of coverage, but it's limited. And if you consider the whole range, this is, by the way, Richardson numbers, gradient Richardson numbers. So they go from very small ones where flow is almost non-stratified to very large one when flow is very strongly stably stratified. So now the question is, why is this so important? If you have such a big scatter, maybe you shouldn't even care about Deacon numbers. And by the way, they are not even being taught in meteorology courses anymore, because it's very difficult to handle them, both theoretically and experimentally. So now I can show you that they are important. This is the Thorpe model run versus large eddy simulation of the stably stratified atmospheric boundary layer. A large eddy simulation is this line, and here you have this is results using the QNSE model, and this is using these 2 other models. You can see that there is a big difference. There is a big warm bias near the ground, and the effect of the parameterization of the surface layer goes way up high. It's 150, 160 meters. It's edge of the boundary layer. So it affects the temperature distribution everywhere here. Now, the warm bias is a very tricky thing, because if you are not careful, you may attribute it to the global warming, right? But this is not a global warming. This is just poor physics. Now, there's some comparison which were done with, so now we looked into comparison different models which are employed in WRF, and wanted to study, to compare several closure models and to see how they compare versus against each other. So the models were Mallory-Yamada-Janich model, which is a very old model being used forever, and QNSE is a relatively new model. It's our model, and we just run simulation side by side and try to see how they perform against each other. There is a lot of papers. People are just running models, publish papers, and they try to see how close the data is to the measurements. But there is almost no studies trying to understand why there is a difference between different models. So Esamati undertook the study, and he tried to see why the models are different, not how close they are to the experiment. So he wanted to see how important are stability functions for the accuracy of the weather prediction. And he used 12 stations in Canada and sounding also data from cases 99 and 97 and 99. Now, one thing I will show you, this is stability function from QNSE, it's in green, and Miller-Yamada-Yanich in blue. And you can see that for large Richardson number, this Miller-Yamada-Yanich go to 0. They just chop off turbulence. It's equivalent to the existence of critical Richardson number for which turbulence disappears. In QNSE model, turbulence never disappears, even very strong stratification. This is relatively new result. We published it like 5-6 years ago, and people more and more begin to appreciate that really critical Richardson number really doesn't exist, and so this kind of formulation becomes very popular now. I will skip the other comparisons because I just don't have time. I'll go and show you conclusions of this research. So QNSE stability functions were found to provide the best near-surface results for virtual temperature. We still have some biases for RMS errors for virtual temperature. The value of neutral Prandtl number, which is a ratio of viscosity to diffusivity, in neutral condition, you can change different parameters for this number, and sometimes it may be more important than all other parameters, and it's really there is a spread, and we don't know which value is better. The theoretical value and what we measure in the laboratory is about 0.7, but what we see in numerical weather predictions, the 0.1 seems to be working better. Now, well, the turbulent kinetic energy program in QNSE gives too high turbulent kinetic energy at high wind speed, and this has effect on eddy diffusivity coefficient. So, as I said, the choice of stability function at the surface layer affects not only near surface quantities but also vertical profiles into the boundary layer. So this is our boundary layer research. Now, what do we do about the jets? This is Jesse was working. He went to University of Rome for a couple of years ago. This is our collaborator, Stefania Espa. She runs the laboratory. This is little Stefania Espa, is Luisa, and Gabriela Denita is a former graduate student, and she just graduated. So they're closely working with Jesse. Our motivation here was to study zonal jets in laboratory, but to derive information on planetary atmospheres and oceans. We studied the westerly jets, which means they go from west to east. I'm saying nonsense. The westerly jets, this is the jets go from west to east. They're typical for the Earth's atmosphere, also for Antarctic circumpolar currents. Easterly jets, or striations are sometimes called, they're emanating from beta plumes in the ocean, and they go from east to west. On giant planets, you have mixture of, it's a mixed bag, they go both ways. Here, what we have is a Rossby wave elasticity, which plays a prominent role in dynamics of jets. Rossby wave elasticity means that you conserve potential vorticity, so if you go along the constant latitude, you don't change potential vorticity, but when you go north or south, you develop returning force, which will take your particle, try to put it back, and then you develop an oscillation. You have a combination of two-dimensional, quasi-two-dimensional turbulence and waves, and they produce very interesting jigsaw puzzles of flows. Waves and turbulence coexist on all scales, and there is no true scale separation, so it's a very difficult problem for modeling. There is Michael McIntyre in Cambridge. He used to say that there is no turbulence without waves. He always tells me this thing. So here we wanted to see and to show that also there is no waves without turbulence, and this is what we did in the laboratory. So now, very important parameter is the rate of inverse cascade, epsilon. This is true nonlinear parameter because it tells us how different scales exchange energy between themselves. So it goes back to the flows in Jupiter. We know that there are jets. You can model them as a simple combination of parabolic flows. And there is a theory which goes, again, back to Michael McIntyre, David Ritchell, and Phil Marcus was doing this. They were saying that they correspond to the stepwise distribution of potential vorticity. And the jumps in potential vorticity correspond to eastward jets, and where they are broad, the potential vorticity is broad and kind of well mixed. So the emphasis is made on monotonic potential vorticity profile or stepwise profile. Now, is it a place to inverse cascade in this flow? Well, we collected data from Jupiter. It's a real data from Cassini. I had 4 days of data. We built a spectra of kinetic energy of zonal energy and non-zonal energy. The zonal energy develops spectrum like n to -5. Non-zonal has a spectrum of Kolmogorov. It's -5/3. We also computed the energy transfer, and we found that it does correspond to inverse energy cascade. So there is inverse cascade. There is epsilon. So is it any way we can find this epsilon without computing the spectrum? Because some planets you just cannot get the spectrum. Jupiter we were lucky, but we were waiting for a very long time. Now, of course, it's a lot of details here. There is an analogy between Rossby wave elasticity and elasticity due to stable stratification. In one case, it's called the Phillips effect. It's when you have stable stratification, and due to mixing, if you go and measure it, you will see that the salty, in this case, salty water stratification is due to salt. Salty water goes into layers. It's a layer structure. And you can liken this layer structure in stratified flow to jet structure in flows with potential vorticity. Now, there is a way to compute epsilon from the layer structure using so-called Thorpe scale. What does it mean? You take the profile of density, it's a vertical profile of density, and this is stably stratified fluid, but because of turbulent mixing, you see that profile of density is not exactly monotonic, so because you have some mixing here. So what Thorpe is trying to do, he takes points and reshuffles them in such a way that the profile becomes monotonic in the end. So this is a Thorpe sorting procedure. Now, the points which are not on this profile in the beginning, you can compute what will be how much they need to be moved up or down to get to this profile. If you create RMS from this reshuffling, you will obtain a length scale, which is called the Thorpe scale. And the Thorpe scale apparently is the same as, very close to the Osmedov scale, which I showed before. Let me show it again. It's here. It's epsilon, which is, in this case, it's a direct cascade, so it's a rate of dissipation. Brand-Fasella frequency to the power of 3 to the power of 1/2. So if you know this scale and you know n, then you can measure the rate of dissipation. Okay, so the experiment shows that the Thorpe scale is confined between 1/4 to 4 times of the Osmedov scale. And in fact, it's very close to the Osmedov scale. So very often, if you go and do this procedure of Thorpe, you will find the Thorpe scale and then Osmedov scale, and then you will get dissipation without measuring it by directly, which is very difficult to do, particularly in the ocean. You can do it in the laboratory, but in the ocean it's a very hard task. So the question is, can we use the same procedure for the jets and to use analogy between stratification and conservation of potential vorticity and develop a scale similar to the Thorpe scale? And missing all the fonts here. But there is equivalent scale in turbulent flow with beta effect, which is epsilon divided by beta q. Beta is beta from beta effect to the power of 1/5, which means the same thing. It's a scale at which the period of Rossby waves is equal to the period of turbulence. So if we can identify the scale, perhaps we can monotonize profile of potential vorticity and find this scale, and then we can find rate of inverse cascade. Okay, so this is why we went into laboratory setting. So we did experiments with the easterly jet. And we try to do the monotonizing potential vorticity and find connection between Lm, it's a new scale, and L beta, which I just showed you. And experiments were done in the University of Rome. So this is a facility which you use. It's a rotating tank. It's only about 1 meter long. You have some lamps here. It's all covered. It looks like this chamber of the Wizard of Oz, but it's covered in black. And when it works, it's completely covered. Why we do this? Because the working area is here. There is a fluid. It takes a parabolic shape because of the rotation of this system. And the parabolic shape provides beta effect to this flow. Now, how do we measure velocities? That's a problem. So what we do is put small styrene particles on the surface of this thing and put it on the background of black paper here. And when it rotates, there is lamps here, and you can follow the particle trajectories. So, in fact, what we do here, it's the same way as we measured velocity with Cassini on Jupiter. It's really amazing, you know, how much similarity you can use between the tools you use for large-scale and small-scale research. Now, it's a forced flow. Amelia was talking about how forcing is important, temperature and everything else. The forcing is really the thing which drives the entire atmospheric, oceanic, and planetary systems. So we needed to put some small-scale forcing in this thing. So how did we do this? We put electric current, there are some electrodes here, and magnets. We put some salt in the water, so it became electrolytic solution. There were some magnets on bottom, with small magnets, which provided magnetic field. So what you do, you create electromagnetic force, and if you place magnet in arc, then you can create, you can introduce linear impulse and momentum impulse, and you can create a jet, and then you emulate beta jet, sorry. So since I'm running kind of very short on time, I'll just tell you that we put the magnets in the arc of 90 degrees, so that we shall have one force sector and 3 unforced sector. So we can study not only force flow, but also unforced flow and mixed flows, so that we can see how turbulence decays with the space. And I will keep the details of it. So we have 3 experiments here, and with these 3 experiments we run the facilities of this device because it was really small and we needed a big range of parameters. So we couldn't do anything else because there are various limitations of